Get that out for me. Did I collect the demonstrate your understandings again?
No.
Mr. Hobby, can you grab those really quick? I'll grab. So, while you get your textbook pages out, I'll grab the demonstrate your understandings. They all just finished. Bob. Not the ones I've already scored. You can keep that one, Dave. I already have a scan of it. You grabbing those in the back corner? Sure. Thank you.
No problem.
The samesies textbook pages that we were working on. Remember how we had the, we cut out those cards on, what was it, Monday? Someone already grabbed it? You already grabbed them? Perfect. And can you make scans, Mr. Hobby, of the two that we didn't have? Yes. I don't, but if you want to go run to the bathroom and get a tissue, you can. All right. So this is the samesies task that we did. So we're looking at equivalence with linear, exponential, and quadratic functions, and then connecting forms of quadratic equations with features of graphs. That's today. That was my favorite lesson. Mr. Hobby and I worked to actually tweak it just a hair, try to make it a little bit better for y'all. So we'll see how that goes. Now, remember, identifying functions, we've done all these things. What we're about to do is going to help support that, but hopefully, at the end of today, all of us can have, by your demonstrating understandings, have everything marked off for the target, foundation and target. We'll see. I'll give you feedback and see if there's anything I'm missing. As a quick reminder, functions with constant rates of change. Davis, what am I talking about when I say a function with a constant rate of change? Linear. Do you agree with that, Davian? Function with a constant rate of change, is that linear? Yeah? Anybody want to add on to or push back on a function with a constant rate of change being linear? Say that one more time. Just an additive rate of change? Constant additive rate of change. Okay, cool. So a linear function has a constant additive rate of change. So is Davis correct that when we say constant rates of change, we're talking about linear? Why do you say no? Oh, so there's not just one function with a constant rate of change. There's how many? There's two of them, right? Davis, the first one is what? Linear, but we need to be careful because that linear has what type of constant rate of change? Constant additive. And Kennedy, the other one was exponential, right? Do you remember what kind of rate of change that exponential has? What? Multiplicative? Is that what you're saying? Okay, constant multiplicative, there we go. So, constant additive versus constant multiplicative. Kyron, do you remember what we call that constant multiplicative rate of change? It's a constant something. Does that help jog your memory? Okay, let me ask you this. Shadidra, what would I call 3 and 2 in respect to the number 6? 3 and 2 are the what? Factors of 6? Because what do I do with factors? What do I do with factors? Multiply them? So Kyron, does that help jog your memory on what a constant multiplicative rate of change is? Huh? Constant multiplicative rate of change. What's that name? It's a constant something. What do we call these things right here? I mean, we are multiplying, but what do we call the 3 and just the 2 without the multiplication? What does Shadidra to call them? Factors. So what do we call the things we constantly multiply by? Constant. Got to remember this language, right? If I say constant factor, we need to know that's that multiplicative rate of change, yeah? Go with that? Okay, so Kelly, remind me, what's that constant additive rate of change called? The constant additive rate of change. What do we call that? Not sure? Or did you say something? No? Okay, let me ask y'all this, and I'm going to come back to you, so use this as a hint. Brianna, constant additive rate of change is what type of function? Linear, right? Do you remember what we call the rate of change for a linear function? So it is constantly adding, but there's a name for that constant additive rate of change. What was it? Slope, right? Remember, don't forget, I know we're trying to make connections across these things. When we talk about a constant additive rate of change, we're talking about its slope, right? rise divided by run, change in y divided by change in x. We want to know all these things so that we can create two variable equations, graph, and create tables for linear and exponential. Alright, samesies. Wrapping all this up really quickly. How did we know that all 5 of these representations were equivalent? So we want to remember this idea of equivalence. Where are all my erasers? There's one behind you, I believe, Mr. Hobby. There should be a 4th one somewhere. I don't know. You'll find it.
It's right here.
Thank you. All right. Why were all 4 of these equivalent? Okay. So are they all quadratic? Yes. But are all quadratics equivalent? No. So I mean, how do we know this is quadratic? It's a concave down, someone said it? Parabola, right? That shape, that parabola tells us it is quadratic. How do we know this equation was quadratic? X to the second, right? That square tells us quadratic. What about this one though? That doesn't have an x squared. Say again. It does. Where's it have a square? After I distribute, right? X times x gives me what? X squared, right? So remember we can distribute there and use that property. So we're seeing all that these are quadratic. What about this table? What could I have done with this table to determine that it's quadratic? I could have graphed it, 100%. That's one way to see it. In fact, if I take -4, -1, it's right here. And -3, 0, it's right there. -2, -1. -1, -4, and 0, -9. Man, all those points are on that graph. Now this speaks to the idea of equivalence, but I'm going to talk more about that table in a second for why it's quadratic. How does this graphing here show us they're equivalent? There's a key idea I'm looking for. There's some other detail I'm looking for. Can anyone add on to the idea that they have the same points? Same inputs map to the same outputs. Because if they have the same inputs and outputs, but it's not the same inputs mapping to the same outputs, they're not equivalent. But I want them to look different, but tell the same story. Same inputs mapping to the same outputs. We good with that idea? Questions, comments, concerns? Okay. Same inputs mapping to the same outputs, but I want to come back to this table because I want to emphasize this because I want us to be clear on this. We're going to talk about this more with the demonstrating understanding, but how just looking at the table, so I could have graphed it, I could see that parabola, how just looking at the table did I know it was quadratic? Peyton, do you remember what tables are really great for looking at, making sense of? I mean, it is tabular, right? But like, why would I create a table? What could I easily look at in that table? Damia, do you remember? Okay. So remember, patterns are great to look at in tables. What kind of pattern do you think we might be looking for, Peyton? What pattern have we always looked for in linear and exponential? All right, I'm going to come back to it. I want you to come back and figure this out. So let's see. All right, what kind of pattern are we looking for in this table? Well, it is a linear function, but what's the pattern? What about that 2? So we're constantly adding by 2. What's that called? It's constant additive. When we talk about a pattern, we're talking about the what? So in this case, constant additive rate of change, but just in general, that last little bit, the rate of change, right? If we're talking about that pattern, we want to see what, Drake? Rate of change, right? And so I see that constant additive rate of change. When I look at, I'm going to come back here, what do I see in this table? Multiplicative, right? Constantly multiplying by 2, okay? So let's go all the way back to this one. What do I need to look at in this table to know it's quadratic? Elizabeth? What do I need to look at in this table? The pattern, but what are we going to call that pattern? I want to see the, there we go, right? I want to look at the rate of change. I can make a graph, sure. But what's happening when you go from -1 to 0? Adding by how much? 0 to -1? -1 to -4? Now that's definitely not constant, is it? But let's continue looking at it. What's happening when you go from 1 to -1? -1 to -3? So that is constant additive, isn't it? And so that's what we want to recognize is that's constant additive. And so what is this rate of change? What type of function had a constant additive rate of change? A linear. So what is this rate of change? Linear, what are we doing? Adding. So linear additive rate of change. And this is what type of function? Quadratic. Let's continue to see this. We actually talked about this with Gold Rush. We're going to continue to look at this. We looked at it on Friday with Dr. Johnson. We're going to look more at these quadratics, but let's look to see if this pattern holds up. So again, I got constant additive. So what's this rate of change? Linear additive, right? Rate of change. Notice there's also symmetry around this point. Remember how a parabola has a line of symmetry? Okay? Last one I want to look at is this one. Okay? Now, not last one I want to look at. I want you to notice, see how there's a huge gap from -4 to 0? And then it goes by ones here. So I actually don't want to look at this one for my rate of change. I need the same change in my inputs to make sense out of it. So that would not be a good one to look at. Let's see if there is another one. Nope, that's the only one. But there is a pattern there that a quadratic function has what type of rate of change? Did it have a constant additive rate of change? Had a... Mr. Hobby, can you pass out the proficiency scales that I had you print out this morning? Okay. That's the toughest part to see with quadratics. Quadratics are easy to see in the equation, they're easy to see in the graph, but we do want to note a linear additive rate of change in those tables. And then the idea is that the same inputs map to the same outputs. So literally you can substitute inputs in, get outputs out. I'm going to give you a chance to write some notes to yourself in a minute if you want. But the last thing I want to point out here is this relation. You'll notice, what word did I not use to talk about this relation right here? What word did I not use for this relation? There's an F word. I didn't call it a function. Why not? It's not a function. In lots and lots and lots of places, one input is mapping to two outputs, at least more than one, right? I can see it right there. 0 maps to both 2 and -2. -1 maps to both of those. 1 maps to both of those. And those are just a couple of the points, right? So we want to recognize, I didn't call it a function because it's not. It's what, Jaden? It's a relation still, but it violates that rule, the defining characteristic of a function. All right. What questions do you have about equivalence, linear, exponential, and quadratic before I let you do some notes to your future forgetful self? Okay. If I were you, and I assume you have some room on, well, there's two places. That's not what I want. Either you can do some notes to yourself on this page 33, okay? about the idea of equivalence and linear, exponential, or quadratic, or the Frere model with the check your understanding on the types of functions, I would do some notes there. Or if you prefer your own notebook for notes, go for it. But any of those places, update, add any notes that you need to for your future forgetful self so that you can have these to study from later. Can I borrow that real quick? This is what I was referring to when I say that identifying linear, exponential, and quadratic, right? So this Frere with check your understanding, right? It has graphs, it has tables, it has equations. This is where I would do my notes to my future forgetful self, personally. You can actually access these lessons later to help you study and things like that, okay? So, everyone who has an iPad, I would get it out and log in, but you only want one during the activity. You ready to kick it off?
I think so.
All right, let's get, yes, Timothy. Okay, I got an extra for you. What's wrong? Oh, that's because I changed it after I created these. Mr. Javi and I changed some things, so I forgot I deactivated that. My bad. All right, I had it somewhere though. Found it. That's it. All right, guys, the code is now on the board. That code is correct.
Everyone's getting logged in. We're getting logged in.
Who needed this?
Awesome. All right. So, Ms. Kenny's been talking to you a lot about a lot of kinds of different functions. We talked about linear, we talked about exponential. We really haven't delved deep into quadratics. What do we know about quadratics so far, guys? What have we been learning about? Parabola, right? We know the shape. We know the journey going to make a shape of a parabola. What do we know about parabola? Can it go like this? Yeah. Can it go down?
Yeah.
What do we call these again? Concavity, right? We call this concave up, smiley face, concave down, frowning face. Great. There's actually a lot of very interesting things we can learn about quadratics past this. And we actually have a lot of forms that we can look at quadratics at. Can anyone give me one of the forms that we've learned about? Does anyone remember? I think we talked about it last week. Maybe not. All right. So there are quite a few different forms.
Mentioned it for like 20
Yeah, I think it was like 20
total.
seconds. Yeah, totally. So I'm not gonna, jump into the sharks and give you all three, but there should be one that looks familiar to most of us. That should be ax squared plus bx plus c. Does it look familiar to anyone? Should have been exposed to this. Great. Does anyone know what we call this form? Well, it's a standard form, yeah. So this is the first form we'll be talking about today. Now, I want you guys to keep in mind that we do still have x values. Those represent our inputs. F of x will represent our outputs. A, B, and C. We're going to actually notice how these values are actually important. They do determine a lot about the graph, which is nice, but they will actually tell us more than just what the graph makes. We can actually notice some special things about it, and we're going to be spending today investigating those things.
I just want to add and clarify, or add on to something to think about, is when we learned about linear, this was one equation of the line that we studied, right? What is that called? Slope, intercept form, right? And the M and the B are values that we just can find. And these values tell us things, right? What does that 3/4 tell us? The rise divided by the run, or the change in y divided by the change in x, right? This 7 tells me about what? The y-intercept, right? Does anyone remember seeing either this form, so sometimes it's written this way, this is the one I go with, or it is also written this way? Does anyone recognize this equation? What is that called? Yeah, we did. Does anyone remember what x1 and y1 are? They together create a... Oh, it's a what? That's a what? That's a point, right? So we call this a point... Say it again? Point slope, right? Literally it has a point and it has a slope, okay? So what Mr. Hobby is referring to and what we want to do is we want to figure out, right? Literally that's a point and a slope on the graph. How do A, B, and C interact with the parabola on the graph? That's what we're trying to find out today, okay? How do A, B, and C affect those things? So just adding on to that to help build into.
Are we ready to launch, Mr. Kenny?
Yeah.
So
I
you
guess
guys,
we hit. Do you want me to actually pull up the slide, the first slide?
yeah, sure thing.
I got you.
Yeah, so as Mr. Kenny was saying, we have seen how different forms can represent the same thing. And what do we call the same thing again in math? We call them equivalent, right? These are equivalent forms. Now, I was referring to the previous slide.
Oh,
You know what?
sorry.
There you go. Yeah, so as Mr. Kenny was saying, we can have point-slope form, which is what we have up there, and we can have something called slope-intercept form, which is what we've been exposed to most with y equals mx plus b. We're going to look at a couple different forms, including the standard form. Okay, so on each of your guys' iPads, you will see some graphs on Desmos, and you will see some sliders. So what you can see up here is, and you can also see it on your iPads, you will have this is slide 2, by the way, of the Desmos activity. You will see that you have a function, f of x, defined as ax squared plus bx plus c. What form is this in again? In standard form, thank you. So we can see that that function is creating this curve, and we have some sliders here. We have a slider for a, b, and c. Now this first section, I want you to pay very close attention here. The top will tell you what to look for each time. So what we can read up here is that this is the standard form of a quadratic function, and it wants you to make a conjecture about how A affects the parabola. So for this first slide, what slide do you think I should focus on? A, B, or C? I should probably focus on A, right? Because that's what the question is asking for. Okay, so I'd say go ahead and start with this first slide. Go to your vertical surfaces, bring your iPads with you, and see if you can use your iPad. Try to adjust A with the slider, see if you can make some conjectures. Yeah. Yeah. Sorry, I thought you were. I didn't know you were going to look at the first slide. I thought you said you were going to. No, you're. I meant to make more connections. What I will say is, once we figure out when we're going to do this in the first one, maybe it's not let her know, let's have her come in and do the equation now that you get some I think that's a great time. Do you know approximately when you're going to get to?
That is actually going to be pretty soon. Just ask her, yes, I think part of it was Friday. She's more of a heads up. Just ask, or she can say it. Yeah.
That sounds like, that doesn't, we have been told.
When you say did,
Okay.
All right, so looking at slide 3, who can give me a response? Who can give me a conjecture for how they think A affects the parabola? I see a lot of good stuff written. Yes, 8, what'd you put?
When the A value is negative, the parabola is concave down, and when it's positive, the parabola is concave up.
When the value of A is negative, the parabola is concave down. When it's positive, it's concave up. Everyone agree with that? Does everyone see how that's happening? I'm actually realizing what the 9s had here. They had good photos. we can see they actually labeled when A is 3.2, we see that concave up, smiley face, A is negative, concave down, frowny face. Now, I'm noticing that we have a lot of different language coming up towards like the strength, right? We noticed that, you know, negative and positive, it's a good difference, but I noticed we had some certain language here.
Before we talk
Yes.
about the size, I just want to show, just in case you hadn't noticed it, right? So notice every time this A value is positive, that parabola is what? Concave up, right? As soon as I hit, so still concave up, as soon as I hit negative, as soon as I can see it, that parabola is now what? Right? So we want to recognize that that A is controlling the concavity. I just want to be clear on that. All right, let's talk about that language.
Yeah, so I saw someone talks about making the parabola bigger or smaller. We talk about the size of the parabola. I'm loving this idea. We can notice that there's some strength going on. I want to get us exposed to more of the language that we see when it comes to this section. We can kind of think of the strength as a stretch, is the most common way how we call it. Kind of think of it as if your parabola is like a rubber band, a scrunchie, right? The idea is that, let's say you have, I'm pinching the vertex, right? We can think of it as though when my A increases in size, when it increases either more positive or more negative, we can think of it as though we are stretching it. We can think of it as though, can everyone see this representation here? We can kind of see how, if you notice, like look at that arc right down here, if I'm pinching the vertex of the parabola, I can see how I'm pulling it, when I pull it, when I'm making that size greater, I can see that I'm literally stretching it out. And we can kind of see it here, if you don't mind, Mr. Kenny, how if we take our A value and if we increase it, we can kind of see that stretch going out, right? It's getting faster and faster, that increase, we think of it as we're stretching it. Yeah, and the same thing happens in the negative direction, right? Let's say when I have concave down, my vertex is up here, right? Same thing, if I increase the A value and I make it more negative, then I am increasing that intensity, I'm stretching it out.
Was there anything else you wanted to say with that?
Yeah, I'm going now.
Okay. The only thing so one, I wanted to say this. We're going to study one of the other forms that actually makes this super clear. One of the other forms makes it much more clear. But two, one of the things that, I don't know if you'll notice with Mr. Hobby, we need to be careful about this language is, when we talk about a graph, there's two different directions on that graph. What am I referring to? There's one this way. Yeah, but like if I were to draw a line, like how would you describe this line? Horizontal, and then this one would be vertical. And so where this is getting stretched vertically, right, it's steeper, what's happening to it horizontally? It's coming together and shrinking, right? It's compressing. And so there's a couple of details that I want us to be careful about. And so we're going to talk about which one it's actually doing. But if you watched his... why is that word dropping out of my head? Scrunchy, thank you. As he was using that, right, he was stretching it vertically, but is also getting skinnier at the same time.
Yep.
Right, so they are related to each other, and so we'll talk about that more heavily. And so keep that in mind. The last thing I want to point out is be careful about that word size. When we talk about the area, we talk about the size of something, especially if we're talking about area. Area is only for an enclosed space. Right? Can't actually find the area because, Mary, what did you note when y'all zoomed out further and further?
It wouldn't like stop going, like the graph didn't really end.
So there's a really good I word you used.
Oh, infinite?
It's infinite, right? It never stops. There's no real size to it. There's that stretch vertically and stretch horizontally, but it goes for forever, right? So there's no real size to that. What are your questions about that A value?
No.
Okay, we don't have a ton of time, but I do want you to, Mr. Hobby, where did those Ferrer models go? I just want you to make some quick notes about that A value. The ones that you made copies of earlier?
They're on your desk.
Are they? Take those back downstairs. Are they on the back desk?
Oh, I got it. Oh, here we are.
Okay.
There we go.
Thank you. Here, can you pass out half of them while I pass